CIET NCERT presents audiobook Ganit Prakash, textbook of mathematics for grade 8.
Chapter number 1, a square and a cube. On the left side of the page, a QR code is provided, scanning which we can reach out to the additional resources for this chapter. Queen Ratna Manjuri had a will written that described her fortune of Ratnas, precious stones, and also included a puzzle. Her son, Khoisnam, and their 99 relatives were invited to the reading of her will. She wanted to leave all of her Ratnas to her son, but she knew that if she did so, all their relatives would pester Khoisnam forever. She hoped that she had taught him everything he needed to know about solving puzzles. She left the following note in her will. I have created a puzzle. If all 100 of you answer it at the same time, you will share the Ratnas equally. However, if you are the first one to solve the problem, you will get to keep the entire inheritance to yourself. Good luck. The minister took Khoisnam and his 99 relatives to the secret room in the mansion containing 100 lockers. The minister explained, each person is assigned a number from 1 to 100. Person 1 opens every locker. Person 2 toggles every second locker, that is, closes it if it is open, opens it if it is closed. Person 3 toggles every third locker, third, sixth, ninth, and so on. Person 4 toggles every fourth locker, fourth, eighth, 12th, and so on. This continues until all 100 get their turn. In the end, only some lockers remain open. The open lockers reveal the code to the fortune in the safe. There is a question mark which reads, before the process begins, Khoisnam realizes that he already knows which lockers will be open at the end. How did he figure out the answer? Hint provided is, find out how many times each locker is toggled. There is a picture on this page with a pic of Khoisnam and the minister in the mansion. Page number 2. If a locker is toggled an odd number of times, it will be open. Otherwise, it will be closed. The number of times a locker is toggled is the same as the number of factors of the locker number. For example, for locker #6, person 1 opens it, person 2 closes it, person 3 opens it, and person 6 closes it. The numbers 1, 2, 3 and 6 are factors of 6. If the number of factors is even, the locker will be toggled by an even number of people and it will eventually be closed. On the right side, there is a block in which number 6 is written and below it 1 into 6 is mentioned, below that 2 into 3, and below that we have factors are 1, 2, 3 and 6. Note that each factor of a number has a partner factor, so that the product of the pair of factors yields the given number. Here 1 and 6 form a pair of partner factors of 6 and 2 and 3 form another pair. Does every number have an even number of factors? There are 3 blocks in different colors here. First one reads 1, that is equal to 1 into 1. The only factor is 1. And in the second block, we have number 4 with factors 1 into 4, 2 into 2. Factors are 1, 2 and 4. And in the third block, we have 9 with factors 1 into 9, 3 into 3. Factors are 1, 3 and 9. We notice in some cases like 2 into 2 that the numbers in the pair are the same. Can you use this insight to find more numbers with an odd number of factors? For instance, 36 has a factor pair 6 into 6, where both numbers are 6. Does this number have an odd number of factors? If every factor of 36 other than 6 has a different factor as its partner, then we can be sure that 36 has an odd number of factors. Check if this is true. Hence, all the following numbers have an odd number of factors. 1 into 1, 2 into 2, 3 into 3, 4 into 4 and so on. A number that can be expressed as the product of a number with itself is called a square number or simply a square. The only numbers that have an odd number of factors are the squares because they each have one factor which, when multiplied by itself, equals the number. Therefore, every locker whose number is a square will remain open. Page number 3. Write the locker numbers that remain open. Khoisnam immediately collects word clues from these 10 lockers and reads. The passcode consists of the first 5 locker numbers that were touched exactly twice. Which are these 5 lockers? The lockers that are toggled twice are the prime numbers, since each prime number has 1 and the number itself as factors. So, the code is 2, 3, 5, 7, 11. 1.1 square numbers. Why are the numbers 1, 4, 9, 16 and so on called squares? We know that the number of unit squares in a square. The area of a square is the product of its sides. The table here gives the areas of squares with different sides. Here there is a tabular column which consists of 2 columns. The first column reads about side lengths in units and the second column is about area in square units. In the first row we have 1 and in area 1 into 1 is equal to 1 square unit. In the second row the side length is 2 units and area is 2 into 2, that is equal to 4 square units. In the third row, side length mentioned is 3 units and area is 3 into 3, that is equal to 9 square units. In the fourth row, the side length mentioned is 4 units and its area is 4 into 4 is equal to 16 square units. In the fifth row, the side length given is 5 units and the area is 5 into 5 is equal to 25 square units. And in the last row, we have 10 as the side length and corresponding area is 10 into 10 is equal to 100 square units. On the right side of this table, we are provided with 5 by 5 square grid which is blank. We use the following notation for squares. 1 into 1 is equal to 1 square, that is equal to 1. 2 into 2 is equal to 2 square, that is equal to 4. 3 into 3 is equal to 3 square is equal to 9. 4 into 4 is equal to 4 square, that is equal to 16. 5 into 5 is equal to 5 square is equal to 25. And so on. In general, for any number n, we write n into n is equal to n square, which is read as n squared. Can we have a square of side length 3 upon 5 or 2.5 units? Yes. Their area in square units are 3 upon 5 whole square, that is equal to 3 upon 5 into 3 upon 5, that is equal to 9 upon 25. And 2.5 whole square is equal to 2.5 into 2.5, that is equal to 6.25. Page number 4. The squares of natural numbers are called perfect squares. For example, 1, 4, 9, 16, 25 and so on are all perfect squares. Patterns and properties of perfect squares. Find the squares of the first 30 natural numbers and fill in the table given here. We are provided with a table here in which we have some numbers written with the squares. First one is 1 square is equal to 1, 2 square is equal to 4, 3 square is equal to 9, 4 square is equal to 16, 5 square is equal to 25. For 6 square is equal to how much we are supposed to fill there. For other numbers also till 30 natural numbers. What patterns do you notice? Share your observations and make conjectures. Study the squares in the table provided. What are the digits in the units places of these numbers? All these numbers end with 0, 1, 4, 5, 6 or 9. None of them end with 2, 3, 7 or 8. If a number ends in 0, 1, 4, 5, 6 or 9, is it always a square? The numbers 16 and 36 are both squares with 6 in the units place. However, 26, whose units digit is also 6, is not a square. Therefore, we cannot determine if a number is a square just by looking at the digit in the units place. But the units digit can tell us when a number is not a square. If a number ends with 2, 3, 7 or 8, then we can definitely say that it is not a square. Write 5 numbers such that you can determine by looking at their units digit that they are not squares. The squares 1 square, 9 square, 11 square, 19 square, 21 square and 29 square all have 1 in their units place. Write the next two squares. Notice that if a number has 1 or 9 in the units place, then its square ends in 1. Let us consider square numbers ending in 6. 16 is equal to 4 square, 36 is equal to 6 square, 196 is equal to 14 square, 256 is equal to 16 square, 576 is equal to 24 square and 676 is equal to 26 square. Page number 5. Which of the following numbers have the digit 6 in the units place? First one, 38 square. Second, 34 square. Third, 46 square. Fourth, 56 square. Fifth, 74 square. Sixth, 82 square. Find more such patterns by observing the numbers and their squares from the table you filled earlier. Consider the following numbers and their squares. 10 square is equal to 100, 20 square is equal to 400, 40 square is equal to 800. In 10, 20 and 40, we notice we have only one zero. But in the squares of these numbers, we have two zeros. Similarly, for 100 square is equal to 10,000, 200 squares is equal to 40,000, 700 square is equal to 49,000, 900 square is equal to 81,000. In these numbers, we notice that 100, 200, 700 and 900 we have two zeros. And in the squares of these numbers, we have four zeros. If a number contains three zeros at the end, how many zeros will its square have at the end? What do you notice about the number of zeros at the end of a number and the number of zeros at the end of its square? Will this always happen? Can we say that squares can only have an even number of zeros at the end? What can you say about the parity of a number and its square? Perfect squares and odd numbers. Let us explore the differences between consecutive squares. What do you notice? 4 minus 1 is equal to 3. 9 minus 4 is equal to 5. 16 minus 9 is equal to 7. 25 minus 16 is equal to 9. See if this pattern continues for all the next few square numbers. From this, we observe that adding consecutive odd numbers starting from 1 gives consecutive square numbers as given here. 1 is equal to 1. 1 plus 3 is equal to 4. 1 plus 3 plus 5 is equal to 9. 1 plus 3 plus 5 plus 7 is equal to 16. 1 plus 3 plus 5 plus 7 plus 9 is equal to 25. 1 plus 3 plus 5 plus 7 plus 9 plus 11 is equal to 36. And this has been pictorially represented on this page with the help of dots. Page number 6. Do you remember this pattern from grade 6? The picture given here explains why each subsequent inverted L gives the next odd number. We have pictorial representation for 1 plus 3 as 1 dot and 3 dots in inverted L shape. And Similarly, for 1 plus 3 plus 3 plus 2 within brackets, we have pictorial representation as 1 and 3 dots in one L shape and 3 dots again in L shape and 2 more dots representing the pattern 1 plus 3 plus 3 plus 2 within brackets. Similarly, we have pictorial representation for 1 plus 3 plus 5 as 4 dots outside the L shape and L shape has 5 dots. Similarly, we have another pictorial representation for 1 plus 3 plus 5 plus within brackets 5 plus 2 and a pictorial representation for the same is provided here. Likewise, we have pictorial representation for 1 plus 3 plus 5 plus 7 also given here and the inverted L shape has 7 dots which are represented in the shape of inverted L. We notice that the sum of the first n odd numbers is n square. Alternatively, every square is a sum of successive odd numbers starting from 1. In mathematics, sometimes arguments and reasoning can be presented without any words. Visual proofs can be complete by themselves. Also, we can find out whether a number is a perfect square by successively subtracting odd numbers. Consider the number 25. Successively subtract 1, 3, 5 and so on until you get or cross over 0. 25 minus 1 is equal to 24. 24 minus 3 is equal to 21. 21 minus 5 is equal to 16. 16 minus 7 is equal to 9. 9 minus 9 is equal to 0. This means 25 is equal to 1 plus 3 plus 5 plus 7 plus 9 and is thus a perfect square. Since we subtracted the first 5 odd numbers, 25 is equal to 5 square. Using the pattern given here, find 36 square. Given that 35 square is equal to 1225. From the question, we know that 1225 is the sum of the first 35 odd numbers. To find 36 square, we need to add the 36th odd number to 1225. How do we find the 36th odd number? The first odd number is 1, second odd number is 3, third odd number is 5, sixth odd number is 11 and so on. What is the nth odd number? The nth odd number is 2n minus 1. Therefore, the 36th odd number is 71. By adding 71 to 1225, we get 1296, which is 36 square. Consider a number such as 38, that is not a square, and subtract consecutive odd numbers starting from 1. 38 minus 1 is equal to 37. 37 minus 3 is equal to 34. 34 minus 5 is equal to 29. 29 minus 7 is equal to 22. 22 minus 9 is equal to 13. 13 minus 11 is equal to 2. 2 minus 13 is equal to minus 11. This represents that 38 cannot be expressed as a sum of consecutive odd numbers starting with 1. Page number 7. Thus, we can say that a natural number is not a perfect square if it cannot be expressed as a sum of successive odd natural numbers starting from 1. We can use this result to find out whether a natural number is a perfect square. Find how many numbers lie between two consecutive perfect squares. Do you notice a pattern? How many square numbers are there between 1 and 100? How many are between 101 and 200? Using the table of squares you filled earlier, enter the values given here, tabulating the number of squares in each block of 100. What is the largest square less than 1000? Here we are provided with blank spaces for writing the numbers between 1 and 100, 101 to 200, 201 to 300, 301 to 400, 401 to 500. Similarly, in between 501 to 600, 601 to 700, 701 to 800, 801 to 900, 901 to 1000. Perfect squares and triangular numbers. Do you remember triangular numbers? Here, dots have been arranged to represent triangular numbers. For 1, we have a 1 dot. For 3, we have 3 dots arranged in a triangular pattern. And in the next picture, we have 6 dots arranged in a triangular pattern. Similarly, for number 10, we have 10 dots arranged in a triangular pattern. And in the next, we have 15 dots arranged in a triangular pattern. Can you notice any relation between triangular numbers and square numbers? Extend the pattern given here and draw the next term. We have here in the next picture 1 plus 3 is equal to 4, that is equal to 2 square. We have a picture in which one single dot is there in a square and other 3 dots are in the remaining part of the square, representing 1 plus 3 is equal to 4. That is equal to 2 square. In the next picture, we have 3 plus 6 is equal to 9, that is equal to 3 square. In this picture, we have 3 dots in a separate L shape and 6 dots in the remaining part of the square. In the next picture, we have 6 plus 10 is equal to 16, that is equal to 4 square. Here, we notice that 6 dots are in a separate part of a square and 10 dots in the remaining part of the square, explaining 6 plus 10 is equal to 16, that is square of 4. We are expected to draw the pattern for the next square number in the blank space provided in the shape of a box. Square roots. The area of a square is 49 square centimeters. What is the length of its side? We know that 7 into 7 is equal to 49 or 7 square is equal to 49. Page number 8. So, the length of the side of a square with an area of 49 square centimeters is 7 centimeters. We call 7 the square root of 49. In general, if y is equal to x square, then x is the square root of y. What is the square root of 64? We know that 8 into 8 is 64. So, 8 is the square root of 64. What about minus 8 into minus 8? That is 64 too. 8 square is equal to 64 and minus 8 whole square is also 64. So, the square root of 64 are plus 8 and minus 8. Every perfect square has two integer square roots. One is positive and the other is negative. The square root of a number is denoted by a symbol for square root. Thus, square root of 64 is equal to plus or minus 8 and square root of 100 is equal to plus or minus 10. Note that square root of 8 square is equal to plus or minus 8 and square root of 10 square is equal to plus or minus 10. In general, square root of n square is equal to plus or minus n. In this chapter, we shall only consider the positive square root. I repeat, given a number such as 576 or 327, how do we find out if it is a perfect square? If it is a perfect square, how can we find its square root? We know that perfect squares end in 1, 4, 9, 6, 5 or an even number of zeros. But it is not certain that a number that satisfies this condition is a square. We can clearly say that 327 is not a perfect square. However, we cannot be sure that 576 is a perfect square. First point, we can list all the square numbers in sequence and find out whether 576 occurs among them. We know that 20 square is equal to 400. We can find squares of 21, 22, 23 and so on until we get 576 or a number greater than 576. 20 square is equal to 400. 21 square is equal to 441. 22 square is equal to 484. 23 square is equal to 529. 24 square is equal to 576. However, this process becomes inefficient for larger numbers. Second point, recall that every square can be expressed as the sum of consecutive odd numbers starting from 1. Consider square root of 81. 81 minus 1 is equal to 80. 80 minus 3 is equal to 77. 77 minus 5 is equal to 72. 72 minus 7 is equal to 65. 65 minus 9 is equal to 56. 56 minus 11 is equal to 45. 45 minus 13 is equal to 32. 32 minus 15 is equal to 17. 17 minus 17 is equal to 0. From 81, we successively subtracted consecutive odd numbers starting from 1 until we obtained 0 at the 9th step. Therefore, square root of 81 is equal to 9. Can we find the square root of 729 using this method? Yes, but it will be time consuming. Page number 9. Third point, we know that a perfect square is obtained by multiplying an integer by itself. Will looking at a number's prime factorization help in determining whether it is a perfect square? Yes, if we can divide the prime factors of a number into two equal groups, then the product of the prime factors in either group combine to form the square root. Is 324 a perfect square? 324 is equal to 2 into 2 into 3 into 3 into 3 into 3. These can be grouped as 324 is equal to within brackets 2 into 3 into 3 into within brackets 2 into 3 into 3. That is equal to within brackets 2 into 3 into 3 square, that is equal to 18 square. We can also write the prime factors in pairs. That is 324 is equal to 2 into 2 within brackets into 3 into 3 within brackets into 3 into 3 within brackets, which shows that 324 is a perfect square. Thus, 324 is equal to within brackets 2 into 3 into 3 whole square, that is equal to 18 square. Therefore, square root of 324 is equal to 18. Is 156 a perfect square? The prime factorization of 156 is 2 into 2 into 3 into 13. We cannot pair up these factors. Therefore, 156 is not a perfect square. Find whether 1156 and 2800 are perfect squares using prime factorization. We can estimate the square root of larger perfect squares by looking at the closest perfect squares we are familiar with and then narrowing down the interval to search. For example, to find square root of 1936, we can reason as follows. First point, 1936 is between 1600, that is 40 square, and 2500, that is 50 square. So, 40 is less than square root of 1936, which is less than 50. Second point, the last digit of 1936 is 6. So, the last digit of the square root must either be 4 or 6. It can be 44 or 46. Third point, if we calculate 45 square, we can compare it with 1936 to half the interval to search from 40 to 50 to either 40 to 45 or 45 to 50. We can write 45 square as 40 plus 5 within brackets into 40 plus 5 within brackets is equal to 40 square plus 2 into 40 into 5 plus 5 square, that is equal to 1600 plus 400 plus 25, that is equal to 2025. Fourth point, 2025 is greater than 1936. So, 40 is less than square root of 1936, which is less than 45. Fifth point, from the observation in point B, we can guess and then verify that square root of 1936 is 44. Consider the following situations. Aribam and Bijo play a game. One says a number and the other replies with its square root. Aribam starts. He says 25 and Bijo quickly responds with 5. Page number 10. Then Bijo says 81 and Aribam answers 9. The game goes on till Aribam says 250. Bijo is now able to answer because 250 is not a perfect square. Aribam asks Bijo if he can at least provide a number that is close to the square root of 250. For this, Bijo needs to estimate the square root of 250. We know that 100 is less than 250, which is less than 400, and square root of 100 is equal to 10 and square root of 400 is equal to 20. So, 10 is less than square root of 250 less than 20. But we are still not very close to the number whose square is 250. We know that 15 square is equal to 225 and 16 square is equal to 256. Therefore, 15 is less than square root of 250, which is less than 16. Since 256 is much closer to 250 than 225, square root of 250 is approximately 16. We also know it is less than 16. Here is another problem that requires estimating square roots. Akhil has a square piece of cloth of area 125 centimeters square. He wants to know if he can cut out a square handkerchief of side 15 centimeters. If not, he wants to know the maximum size handkerchief that can be cut out from this piece of cloth with an integer side length. 125 is not a perfect square. The nearest perfect squares are 11 square is equal to 121 and 12 square is equal to 144. So, the largest square handkerchief with integer side length that can be cut out from this piece of cloth has side length 11 centimeters. Figure it out. Question number 1. Which of the following numbers are not perfect squares? First, 2032. Second, 2048. Third, 1027. Fourth, 1089. Question number 2. Which one among 64 square, 108 square, 292 square, 36 square has last digit 4? Question number 3. Given that 125 square is equal to 15,625, what is the value of 126 square? First part, 15,625 plus 126. Second option, 15,625 plus 26 square. Third option, 15,625 plus 253. Fourth option, 15,625 plus 251. Fifth option, 15,625 plus 51 square. Question number 4. Find the length of the side of a square whose area is 444 meters square. Question number 5. Find the smallest square number that is divisible by each of the following numbers 4, 9 and 10. Question number 6. Find the smallest number by which 9,408 must be multiplied so that the product is a perfect square. Find the square root of the product. Question number 7. How many numbers lie between the squares of the following numbers? First part, 16 and 17. Second part, 99 and 100. Question number 8. In the following pattern, fill in the missing numbers. Page number 11. 1 square plus 2 square plus 2 square is equal to 3 square. 2 square plus 3 square plus 6 square is equal to 7 square. 3 square plus 4 square plus 12 square is equal to 13 square. 4 square plus 5 square plus 20 square is equal to dash square. 9 square plus 10 square plus dash square is equal to dash square. We are supposed to fill up these dashes. Question number 9. How many tiny squares are there in the following picture? Write the prime factorization of the number of tiny squares. Here we are provided a picture of a square with small squares which are 9 in a row and 9 in a column. So in total we have 81 squares, and each square specifically has 25 square grids in one particular square which is represented inside these square. 1.2 Cubic numbers. You know the word cube from geometry. A cube is a solid figure all of whose all sides meet at right angles and are equal. How many cubes of side 1 centimeter make a cube of side 2 centimeters? On the right side of the page, we are provided pictures of two cubes. In one, we have a single cube, and in the other picture, we have 8 cubes which are combining to form a bigger cube. How many cubes of side 1 centimeter will make a cube of side 3 centimeters? Page number 12. Consider the numbers 1, 8, 27 and so on. These numbers are called perfect cubes. Can you see why they are named so? Each of them is obtained by multiplying a number by itself 3 times. We note that 1 is equal to 1 into 1 into 1. 8 is equal to 2 into 2 into 2. 27 is equal to 3 into 3 into 3. Is 9 a cube? We see that 2 into 2 into 2 is equal to 8 and 3 into 3 into 3 is equal to 27. This represents that 9 is not a perfect cube, nor is any number from 10 to 26. On the right side of the page, we are provided with a picture which represents cube of 3 with 27 cubes joined together. Can you estimate the number of unit cubes in a cube with an edge length of 4 units? Here we are provided another cube. The picture represents the unit cubes with 64 unit cubes are joined to represent cube of 4. It has 64 unit cubes. If you notice carefully, each layer of this cube has 4 into 4 unit cubes. Each square layer has 16 unit cubes, that is 4 into 4, and there are 4 such layers. So, the total number of unit cubes is 4 into 4 into 4, that is equal to 64. Since 5 cube is equal to 5 into 5 into 5, that is equal to 125. 125 is a cube. In general, for any number n, we write the cube n into n into n as n cube. Complete the table given here. We have a tabular column in which we have numbers from 1 to 20. For some numbers, the cube is mentioned, and for others, we are supposed to complete the cubes. For example, 1 cube is equal to 1, 2 cube is equal to 8, 3 cube is equal to 27, 4 cube is equal to 64, 5 cube is equal to 125. For other numbers, we are expected to write down the cubes in the tabular column. What pattern do you notice in the table given here? We know that 0, 1, 4, 5, 6, 9 are the only last digits possible for squares. What are the possible last digits of cubes? Page number 13. Similar to squares, can you find the number of cubes with 1 digit, 2 digits and 3 digits? What do you observe? Can a cube end with exactly 2 zeros? Explain. Just as we can take squares of fractions or decimals, 4 upon 6 whole square or 13.08 whole square and minus 6 whole square, we also can compute cubes of such numbers: 4 upon 6 whole cube, 13.08 whole cube and minus 6 whole cube. 4 upon 6 whole cube is equal to 4 upon 6 into 4 upon 6 into 4 upon 6 is equal to 64 upon 216. 13.08 whole cube is equal to 13.08 into 13.08 into 13.08, that is equal to 2237.810112. Minus 6 whole cube is equal to minus 6 into minus 6 into minus 6, that is equal to minus 216. Taxi cab numbers. Once, when Srinivas Ramanjan was working with G.H. Hardy at the University of Cambridge, Hardy had come to visit Ramanjan at a hospital when he was ill. Hardy had ridden in a taxi cab numbered 1729, and he remarked that 1729 was rather a dull number, adding that he hoped that this was not a bad sign. Ramanjan immediately replied, "No, Hardy, it is a very interesting number. It is the smallest number that can be expressed as the sum of two cubes in two different ways. 1729 is equal to 1 cube plus 12 cube, or 9 cube plus 10 cube. Here we are provided with a picture in which we have a scene where Professor Hardy has come to visit Professor Ramanujan lying on the bed. Because of this story, 1729 has since been known as the Hardy-Ramanujan number, and numbers that can be expressed as the sum of two cubes in two different ways are called taxi cab numbers. The next two taxi cab numbers after 1729 are 4104 and 13832. Find the two ways in which each of these can be expressed as the sum of two positive cubes. How did Ramanujan know this? Well, he loved numbers. All through his life, he tinkered with numbers. During Ramanujan's time in Cambridge, his colleagues often marveled at his ability to see deep patterns in numbers that seemed arbitrary to others. His colleague John Littlewood once said, "Every positive integer was one of his Ramanujan's personal friends." Page number 14. Perfect cubes and consecutive odd numbers. Consecutive odd numbers have a role to play with cubes too. Observe the following pattern. 1 is equal to 1 is equal to 1 cube. 3 plus 5 is equal to 8 is equal to 2 cube. 7 plus 9 plus 11 is equal to 27 is equal to 3 cube. 13 plus 15 plus 17 plus 19 is equal to 64, that is equal to 4 cube. 21 plus 23 plus 25 plus 27 plus 29 is equal to 125 is equal to 5 cube. 31 plus 33 plus 35 plus 37 plus 39 plus 41 is equal to 216 is equal to 6 cube. Later, in this series, we get the following set of consecutive numbers. 91 plus 93 plus 95 plus 97 plus 99 plus 101 plus 103 plus 105 plus 107 plus 109. Can you tell what this sum is without doing the calculation? Cube roots. We know that 8 is equal to 2 cube. We call 2 the cube root of 8 and denote this by 2 is equal to cube root of 8. More generally, if y is equal to x cube, then x is the cube root of y. This is denoted by x is equal to cube root of y. So, cube root of 8 is equal to cube root of 2 cube, that is equal to 2. Similarly, cube root of 27 is equal to cube root of 3 cube, that is equal to 3. And cube root of 1000 is equal to cube root of 10 cube, that is equal to 3. In general, cube root of n cube is equal to n. How do we find out if a number is a cube? Taking inspiration from the case of squares, let us see if we can use prime factorizations. Let us check if 3375 is a perfect cube. 3375 is equal to 3 into 3 into 3 into 5 into 5 into 5. Can the factors be split into 3 identical groups? For 3375, we can form 3 groups of 3 into 5. So, 3375 is equal to 3 into 5 within brackets into 3 into 5 within brackets into 3 into 5 within brackets. That is equal to 3 into 5 whole cube is equal to 15 cube. Another way is to check if the factors can be grouped into triplets. 3375 is equal to 3 into 3 into 3 within brackets into 5 into 5 into 5 within brackets. That is equal to 3 cube into 5 cube. This means cube root of 3375 is equal to 15. Is 500 a perfect cube? 500 is equal to 2 into 2 into 5 into 5 into 5. We observe that the factors cannot be split into 3 identical groups. Therefore, 500 is not a perfect cube. Page number 15. Here, we are provided with a table having 2 columns. The first column reads prime factorization of a number and the second column reads prime factorization of its cube. In the first column, we have 4 is equal to 2 into 2 and in the second column, we have prime factorization of its cube. 4 cube is equal to 64. That is equal to 2 into 2 into 2 into 2 into 2 into 2. That is equal to 2 cube into 2 cube. In the next row, we have 6 is equal to 2 into 3. In the second column, we have 6 cube is equal to 216, which is equal to 2 into 2 into 2 into 3 into 3 into 3. That is equal to 2 cube into 3 cube. In the third row, we have 15 is equal to 3 into 5. In the second column, we have prime factorization of its cube. 15 cube is equal to 3375 is equal to 3 into 3 into 3 into 5 into 5 into 5. That is equal to 3 cube into 5 cube. In the last row, we have 12 is equal to 2 into 2 into 3. And in the next column, we have prime factorization of its cube. 12 cube is equal to 1728. That is equal to 2 into 2 into 2 into 2 into 2 into 2 into 3 into 3 into 3. That is equal to 2 cube into 2 cube into 3 cube. Observe that each prime factor of a number appears 3 times in the prime factorization of its cube. Find the cube roots of these numbers. First one, cube root of 64. Second, cube root of 512. Third, cube root of 729. Successive differences. We know that the differences between consecutive perfect squares gives the sequence of odd numbers. Observe the figure here where the differences are computed successively for perfect squares. After 2 levels, all the differences are the same. We have perfect squares here as 1, 4, 9, 16, 25, 36. In level 1, we notice that the difference between 1 and 4 is 3. Difference between 4 and 9 is 5. Difference between 9 and 16 is 7. Difference between 16 and 25 is 9. And difference between 25 and 36 is 11. And in the level 2, we find that the difference between these consecutive odd numbers is always 2. 3 and 5, the difference is 2. Between 5 and 7, the difference is 2. Between 7 and 9, the difference is 2. And between 9 and 11, the difference is 2. Compute successive differences over levels for perfect cubes until all the differences at a level are the same. What do you notice? Perfect cubes 1, 8, 27, 64, 125, 216 and so on. 1.3 A pinch of history. The first known list of perfect squares and perfect cubes are compiled by the Babylonians as far back as 1700 BCE. These lists, found on clay tablets, were used to quickly find square roots and cube roots in problems involving land measurement, architecture design, and other areas where geometric calculations were necessary. Page number 16. In ancient Sanskrit works, the term varga was used both for the square figure or its area, as well as the square power, and the term ghana was used both for the solid cube as well as the product of the number with itself 3 times. The fourth power was called varga varga. These terms were used in India at least from the 3rd century BCE. Aryabhatta 499 CE states, a square figure of 4 equal sides and the number representing its area are called varga. The product of 2 equal quantities is also called varga. Thus, the term varga for square power has its origin in the graphical representation of a square figure. Why is the word root, the root of a plant, used for the mathematical operation under root, that is square root, cube root, etc.? It is because in ancient India, the Sanskrit word moola, meaning root of a plant, basis, cause, origin, etc., was used for the mathematical operations of taking roots. In Sanskrit, vargamoola, the basis, cause, origin of the square, was used for square root, and ghanamoola was used for cube root. This use of moola for the mathematical concept of root was subsequently emulated in Arabic and Latin through their corresponding words for the root of a plant, jidhar and radix, respectively. The term moola for root has been used in India at least from the 1st century BCE. Another term used for pada, that is foot, basis, cause, origin. Brahmagupta 628 CE explains, the pada, that is root, of a kriti, that is square, is that of which it is a square. Figure it out. First question, find the cube root of 27,000 and 10,648. Question number 2, what number will you multiply by 1,323 to make it a cube number? Question number 3, state true or false. Explain your reasoning. First one, the cube of any odd number is even. Second, there is no perfect cube that ends with 8. Third, the cube of a 2-digit number may be a 3-digit number. Fourth, the cube of a 2-digit number may have 7 or more digits. Cube numbers have an odd number of factors. Question number 4. You are told that 1331 is a perfect cube. Can you guess, without factorization, what its cube root is? Similarly, guess the cube roots of 4913, 12167 and 32768. Page number 17. Question number 5. Which of the following is the greatest? Explain your reasoning. First one, 67 cube minus 66 cube. Second, 43 cube minus 42 cube. Third, 67 square minus 66 square. Fourth one, 43 square minus 42 square. Summary. First point, a number obtained by multiplying a number by itself is called a square number. Squares of natural numbers are called perfect squares. Second, all perfect squares end with 0, 1, 4, 5, 6 or 9. Squares can only have an even number of zeros at the end. Third point, square root is the inverse operation of square. Every perfect square has two integral square roots. The positive square root of a number is denoted by the symbol under root. For example, square root 9 is equal to 3. Fourth one, a number obtained by multiplying a number by itself 3 times is called a cube. For example, 1, 8, 27, etc. are cubes. Fifth point, a number is a perfect square if its prime factors can be split into two identical groups. Sixth point, a number is a perfect cube if its prime factors can be split into 3 identical groups. Seventh point, the symbol cube root denotes cube root. For example, cube root of 27 is equal to 3. Page number 18. Puzzle time. Square pairs. We have the following numbers 3, 6, 10, 15, 1. They are arranged such that each pair of adjacent numbers add up to a square. 3 plus 6 is equal to 9. 6 plus 10 is equal to 16. 10 plus 15 is equal to 25. 15 plus 1 is equal to 16. Try arranging the numbers 1 to 17 without repetition in a row in a similar way. The sum of every adjacent pair of numbers should be a square. Can you arrange them in more than one way? If not, can you explain why? We are provided with blank boxes for the same purpose. We are supposed to arrange the numbers from 1 to 17. Can you do the same with numbers from 1 to 32 again without repetition? But this time, arranging all the numbers in a circle. We are provided with square boxes in the form of a circle. And this page has a picture with kids trying to solve the puzzle provided here. Chapter 1 ends here.
Ganit Prakash, you were just listening to this audiobook, textbook of mathematics for grade 8. Narration, Swarnlata Sharma. Sound recordist, Manju Kumari. Production assistant, Kusum Lata. Directed and produced by Vimlesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.